Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are continuing our study of Chapter 7, Equations of State, and we've been looking at cubic equations of state. We're going to look at a different variety in this lecture. Generalized correlations for gases are frequently used. They are based on the theory of corresponding states, which states that all fluids, when compared at the same reduced temperature and reduced pressure, have approximately the same compressibility factor, and all deviate from ideal gas behavior to about the same degree. Now, we could improve this theory a little bit that said all fluids with the same value of the acentric factor, when compared at the same reduced temperature and pressure, have about the same compressibility factor and deviate from ideal gas behavior to about the same degree. And this would improve upon this a bit. So, for instance, if one were to look at the graph of methane, this is the compressibility factor Z, graphed versus pressure, for a variety of temperatures. So very large temperatures, and as we decrease the temperature, we see that it starts sweeping down, and we end up with these various curves. If we look at these for a lot of different materials here, so Z is along the horizontal or the vertical axis, reduced pressure, P sub R. Remember that PR is equal to the actual pressure over the critical pressure, all absolute, and TR is T over the critical temperature, all absolute. So along our lower axis is the reduced pressure, PR, and if we look at these graphs for TR at selected values for many substances, so the ones shown here are methane, ethylene, ethane, propane, and butane, ipentane, N-heptane, nitrogen, carbon dioxide, water, a lot of really common substances, and then average out those answers, we get these curves here. And these are what the generalized compressibility factor is going to approximate, these average values, and it will be very close to what we get in reality for any gas. If we look at, again, the methane graph and then the Lee-Kesler generalized correlations, what we see is that these graphs here look very much like what these are out here beyond the two-phase region. This is our saturation dome. This point right here is the critical point. PR equals 1 and TR equals 1. And that point is the critical point in this reduced temperature and pressure notation. So out here, these curves look very much the same as the methane graph. And then we have these that come in for values below the critical temperature and below the critical pressure. And they go through the saturation region and move on up. So these dotted lines are gas on this side, split into two phases in between, and our liquids going up as we go to higher and higher pressures. So these are liquid compressibilities. The graphs that are in our book for this are shown for omega equals 0, and it's designated Z naught. And again, it's the same basic facts. So Z naught is over here. PR is across the bottom. It is a logarithmic scale, so they count in decades. This is therefore 2, 3, 4, so forth. Okay? This is 0.2, 0.3, 0.4, and so forth. And we have various values of TR. We are going to find our value of P, So let's say that we had P equal to 0.8. No, that's 0.7, excuse me, 0.7. And TR is equal to 1.2. We would find the intersection of those two graphs right here. And then read straight across to the left-hand axis, and that tells us our value of Z naught. That is the compressibility when omega is equal to 0. There is another graph, though, that is the partner to this, that is the compressibility when omega is equal to 1. We will take this value and add the product of this and omega, the acentric factor, to our Z naught to come up with a value of Z. Now this graph is a lot crazier looking, but again we have PR across the bottom here. We have Z1 along the left-hand axis and all the values of TR. Now when you see these ones that come down and then shoot up, that means that we've gone from being a liquid to a gas. So these are the vapors on this side and the liquid on the higher pressure side of those. The ones that just do a kind of a much smoother sweep, those are going to be above the critical point, so they are all vapor-like. Now for the very tiny gases, the quantum gases, the generalized correlations don't work very well in those cases, and so you need to correct the critical temperature and the temperature and critical temperature using these relationships here. So TC for hydrogen is this equation here, 43.6 over 1 plus 21.8 over 2.016 times the temperature. PC is 20.5 over 1 plus 44.2 over 2.016 T. There are similar equations available for helium and neon. You don't need these very often, but when you do, just be aware that those very tiny gas molecules that are very nearly ideal gases, they will require corrections to make the generalized correlations work. Now we want to do an example. The example here is to calculate the Z for N-butane at 110 degrees C and 18.66 bar. The critical properties and omega are given here. We could have found those in a data book. And so what we want to first do is calculate TR and PR. So TR is T over TC, which is 110, that's in degrees C, so add 273 so that it is absolute. Divide that by 425.1. TR is equal to 0.9. PR is going to be our pressure 18.66 bars. That's typically given in absolute, divided by 37.96. And this is approximately 1/2. I recommend that you now stop the video and go look these up on the graph for Z naught and Z1. I found approximate values as follows. Z naught is very nearly 0.7, Z1 is very nearly negative 0.2, and therefore Z is approximately 0.7 plus omega 0.2 times Z1 negative 0.2, and this is approximately negative, or not negative, 0.66. Now you can do a lot better because there are tables available for this, and then you would be able to look these up very much more carefully. There are generalized correlations for many of the other things that we're interested in. Specifically, enthalpy and entropy are of great interest to many of the problems we try to solve. Molar residual enthalpy is graphed also by the Lee-Kesler equations. And here, what you're going to be looking up on the axis on the left is H minus HIG, so that's the residual enthalpy, divided by R over TC. This turns it into a dimensionless quantity. The units are going to be determined by your choice of R. So you'll need to know the critical properties, right, to be able to find TR and PR. And you can look up the residual enthalpy naught and the residual enthalpy superscript 1 and use those in this expression at the top of the page. These are the graphs from your textbook. Remember, though, that this is going to be a dimensionless form of residual enthalpy, and you're going to need to multiply your final answer times R and TC in order to determine the actual value with the desired units. Molar residual entropy is also in here, very similar sort of expression. In order to make this dimensionless, they divide through by R. So its residual enthalpy divided by R is the dimensionless molar residual entropy. We have this for the case where omega equals 0, the case for omega equals 1, and we relate those using this equation to turn it into residual entropy multiplied by R with your choice of units. Let's work another example. We want to find the change in molar enthalpy when propane is heated from 295 Kelvin to 740 Kelvin at a constant pressure of 4.25 megapascals. I recommend that you pause the video and try working this one on your own. First, I found the data. T sub C for propane is 369.9 Kelvin, P sub C is 4.301 megapascals, and the acentric factor is 0.153. T1 will be 295 Kelvin divided by T sub C 369.9, which is approximately 0.8. T2 is 740 divided by 369.9, which is 2. And P1 and P2 are 4.25 megapascals, and that's close enough to 4.301. They called that the critical pressure, and so this is approximately 1. Obviously, they were using a different resource than I was. So next, what we want to look up is H minus HIG over RTC, not at state 1, and H minus HIG RTC 1 at state 1, and the same things for state 2. Now go to the graphs or data table if you have that, and find the approximate values for those. If you have not done so already, pause the video, go look them up. So we have the 2 points marked here. When PR is equal to 1, TR equals 0.8, and TR equals 2. Based on this value, the superscript 1 is approximately, so roughly the values at state 1, the residual over RTC naught is negative 4.5, and 1 is negative 5.2, and at state 2, it's about 0.7 and 0.2. At state 1, adding these up, Z or H naught over the H expression 1 times omega with omega equal to 0.53, this is approximately negative 5.3. And at state 2, our answer is about 0.73. These are going to be my delta H residual, subtracting state 2 minus state 1. And then I'm going to need to figure out what the delta H for the ideal gas is. This is going to be the integral of C sub P dt. This is an outline of the solution as done in the book. So they found their values here, and they've got the H residual using R and T sub C. At state 1 is negative 16,274 joules per mole, and at state 2 is 1,016 joules per mole. Their numbers vary a little bit different from what I looked up on those graphs. They use data from the appendix for C sub P as a function of temperature. This must be integrated with respect to temperature. And when they did that, and I'll trust that they got those numbers right, that was 50,578 joules per mole. So we've gone from real to ideal gas, is this. We've gone from state 1 to state 2 as an ideal gas, is this. And then returning to being the real substance is this value. So we then need to go through and do those calculations, and the sum of these using appropriate signs, because remember, this is negative H residual, we come up with about 68,000 joules per mole. Don't get too crazy. If you're using these values from the graphs, you're really only getting a couple of digits there, so don't worry too much about your precision on all of these calculations. So this concludes this video lesson. We are going to continue our study in the next video. Thank you very much for your time.